This is the ChipCon 1110. It's one of several chips that were afflicted. This is the logo. So if you see the larger chip, and when you zoom in, you see this version of the Swiss flag or this little C moon thing, then you know that it's a ChipCon brand. If you see the gun, it's an Ember brand. These are and this is also the chip that's inside of the IME. So you can check to see what the random numbers are. And there are a bunch skipped between rows. But if I give you a random back-off delay of D376, and then I start generating a key, you know that that key begins with 9D64, 69EB, 4E80, F4E6, and you can keep on going. And as you'll note in this, you just go down diagonally and to the right one in order to figure out what the next byte is. These aren't random at all. If you plot a given byte and its successor byte, this is called a strange attractor graph. These snowflakes are supposed to look like static. If someone had just dumped these numbers and drawn this type of graph, he would have seen how wretched it was. This is from another chip vendor. Pretty much everyone screwed this up, so don't blame ChipCon for it. If you do the wrong pair, like this is a wrong pair and this is a wrong pair, it does look like static. This is an insecure random number generator, but these lower two graphs are what you would expect to find on a secure chip. These upper two graphs are not the least bit secure. On this one, instead of having everything in a loop that's predictable, instead, for any given 16-bit state, there are two possible successor states. You find this by dropping a vertical line through here. So like any x-axis point it crosses the scatter plot at exactly 2 points. You have to zoom in to see that these side lines are not solid. They're skipping bits in between. Because of this, everything that was trusted into the certificates of these devices could be remotely exploited. You can drive by a house and rip the keys out. Now, that's not the same as saying that all of the protection of the devices had gone away, because this was not the interface through which load shedding of the entire house would normally occur. But when mistakes this serious are being made, and they're being made through the supply chain so that they wind up infecting every vendor at once, more attention needs to be paid. And I think that in the case of these particular bugs, the attention should have been paid on the part of the engineers integrating these chips. In addition to whatever pen testing groups you hire externally, you should make sure that your own device engineers have some of their day to sit and beat up the pieces that you've purchased from your suppliers to try to find mistakes in them. Because if you can find it before an attacker can find it, then it can be fixed. And if you don't, then you'll wind up shipping random number generators no better than a single recorded die roll. So in conclusion, start taking things apart. Get a damn Leatherman and take it to everything you buy. If you're buying 100,000 meters, there is no excuse to not take a knife to one. Or 10. And there's no excuse not to have your own engineers looking for mistakes that your suppliers have done. Even though this vulnerability has been published, even though all of these vulnerabilities have been published, I know that these mistakes will be repeated. Because the engineers who are busy building products don't have time in their workday to pay attention to how other products were broken or what mistakes their competitors have made. And if that could be fixed, then more secure devices could be built. But you have to take it apart to see what's inside of it. You have to see how it works. And you have to have a packet sniffer or a radio interface or some way to actually hear what's going on so that you don't have to do everything blind and so that you don't have to trust your salesman. A few things here were in collaboration with other people. But in Multi-Threaded Banjo Dinosaur Knitting Adventure, the banjos were entirely my idea, and neither Fabian Serrer nor Arjen Skepnisse can claim credit for them. The keyboard attack was first implemented by Moser and Schroeder. My extension of it allows it to be performed more promiscuously. And then a lot of the IME work was done in collaboration with Mike Osmond, and all of the comics are from XKCD. Thank you kindly. Are there any questions?
Let me bring you this.
No one interrupted me with a question. I was kind of hoping for it.
Well, so first off, yeah. Okay. I'm Ed Barrowset. I'm with Elster, and we're very happy to see the reports that you're doing, by the way. It's useful because our engineers, I can correct that if I don't have a whole lot of time to go trying to figure out how to make the parts that we buy fail by other than the user that needs temperature, for example. So with that in mind, I mean, some of the things that we are doing and have done, checking random numbers, about that one. But one of the other questions I had for you, though, is what other things? So among the things that we currently do are doing things like clock glitching, power supply glitching, and then just general trying to abuse things. But have you got any particular things that you would recommend that we try that have high potential for payoff?
The most important thing is fuzzing. There are two types of products in the world. There are those that were fuzz tested in development, and there are those that fall over immediately when you send them random traffic with valid checksums. So within your firm, you have the source code to your product. You can build weird tools around it with significantly less cost than an outsider would incur. So one of the things that you can do is you can take your networking stack and you can record all of the valid packets that go across. And then you can start making random changes to them. Flip bits here and there, randomize words, do things like that, and then rebroadcast them, making sure that all of the crypto is correct and that all of the checksums are correct so that the packets won't be dropped. When you do this on any product that was not designed with it in mind, or anything more complicated than a toaster oven's clock, the device falls over. And this is and then paying attention to how and why it falls over and where it falls over can be very effective for finding these problems.
Well, for what it's worth, we actually do fuzz testing of our stuff. Mostly I was asking about the kinds of intrinsic problems with the silicon of the stuff that we buy to incorporate.
So in that case, never trust random number generators that you haven't audited to hell and back. And even then, you probably missed something. The lucky thing is that random number generators that are a little bit bad don't seem to be broken very often. But random number generators that are atrociously written appear commonly. This is how the PlayStation 3 master key was leaked, which allows PlayStation 3 discs to be manufactured without a subsidy being paid to Sony. Always check that part. You should also check to make sure that RAM is erased if you have anything important held in RAM. A lot of the ChipCon devices and the MSP430 devices and similar ones would have a locking mechanism that could be undone if you erased all of flash memory. And the problem here was that they thought that the only valuable things would be in flash memory because that's where your code is. But they forgot that keys would very often be found within RAM. So there's an attack in which you connect a debugger, you erase the chip, which obliterates all of the code. This does not get you a copy of the software. But then when you read out RAM, you can search through RAM to find the keys. This affected old versions of ZStack, but has since been fixed. And it affects any software written for these chips where the author does not know about this weird property of the chip's protection measure. Each one of these things, though, is so specific to one way in which one chip has been broken that while I can give you numbers of individual examples, it's terribly difficult for me to slam a heavy book on your desk and say, this book contains all of those things that you need to look for, or even the most popular ones. I don't think that anyone has done a survey of which recurring vulnerabilities had appeared in which chips.
Could you just take a minute and talk about the GoodFet chip and how people might choose, who are interested in taking apart stuff, poking at it with the chip, and what they might find? Just talk through.
Certainly.
Talk through that.
So the GoodFet is a surface mount kit. It's not the easiest thing to solder, but you can solder it yourself. The parts cost less than $20, and I will give you a board for free. I have some upstairs, and if I run out, I can mail them to you. It's an adapter from Python code on a computer to any sort of target device. And we have more than 20 or 30 drivers at this point. So it's reasonably easy to take, say, a radio board or a microcontroller board, wire a GoodFet into it, and then dump a copy of its software, or packet sniff its radio network. And in doing these things, you can begin to see how these devices work and how they function. If you're not particularly interested in meter vulnerabilities, you can buy all sorts of toys. You can reflash the pink children's toy that I showed you, using the GoodFet to become a radio spectrum analyzer. So then if you're worried about interference on a channel, you can just pop open the radio spectrum, navigate to that channel, and see what's on it. You can see cell phones, you can see meters themselves broadcasting if you'd like to figure out their center frequencies. And all of this comes in a kit that costs less than your lunch. So I suggest that you grab one if you're interested.
We just have a couple minutes left. Are you going to set up back upstairs again so people can see the keyboard sniffing if they want to see that?
Yes, I'll be there for at least the next hour.
And the next session, I think, starts upstairs here in about 5 minutes. So if there's time for one more question, if somebody has an easy one, we'll take that. And if not, all right.
All right.
Thanks a lot.
Thank you kindly.